we shall study perhaps the most obvious example of non-trivial stochastic process that is generated as the output of a linear filter. This is the Gauss Markov process. So we have our filter structure. I'm just gonna draw it out. Where in this case the impulse response h of t is equal to e to the power of constant times t times a Heaviside function. So this is the typical impulse response that you meet when you have a first order differential equation. Now we're going to let this be driven by some kind of noise. Let us use white noise as the input. So we're going to define it like this. So some things to notice there. First, we have these Heaviside functions both in the impulse response, like we actually always have when we have such a first order differential equation. And then we have this Heaviside function in the process, the white noise process, meaning that the process is being turned on at time 0. There is no noise before that. This is how we would like things to have causality. This process V of t, which is, you see, has a autocorrelation function given by a delta function, that's standard white noise. That is a stationary process. And you see that because it's possible to write its autocorrelation function like this. There's no T1 and T2 here. We just write it in terms of the difference T2 minus T2, which we call tau. And then we also have a strength of this white noise called Q. So that's what goes into our system. And then what comes out of the system is, of course, this convolution. So in principle, we go from minus infinity to plus infinity. Even though, of course, the Heaviside functions are going to eliminate that. Okay, so that is the output of this linear system. What I want to find now is I want to find the autocorrelation function of y. To find that, I'm first going to find the autocorrelation function of x, then I'm going to find the cross correlation of xy, and then finally I find the autocorrelation function of y. So first, Rxx, let us look at what that one is. So in general, this is a function of T1 and T2. It's going to look like this. So it's identical to the autocorrelation function of V insofar as both T1 and T2 are greater than 0. Because nothing, we know that x is 0 for t smaller than 0. And clearly cross correlation of 0 or with anything else is going to be 0. And this we can also write in terms of Heaviside functions. We're going to use a lot of Heaviside functions here. So notice also that this is a non-stationary process, because what happens out here with the Heaviside functions is not something you can write as a difference T2 minus T1. So then we are going to do the cross correlation between x and y, and we have some formula for that I just derived in previous blackboard session. So Rxy, T1 and T2. This is the integral from minus infinity to plus infinity of Rxx. And then I have T1 and T2 minus alpha, impulse response of alpha, integrated over alpha. So that is just the standard formula that I took straight from the previous session. Then I need to fill in the details of all these things in my particular case now. Well, first I have, I'm inserting for Rxx. So what do we have here? This is Rxx, and then this is h of alpha, and this part you can recognize as the autocorrelation function of v, evaluated at t2 minus t1 minus alpha instead of tau. So now I'm going to integrate something that involves a delta function over, I'm going to integrate this over alpha, where alpha goes to a delta function. So then I use the shifting property of delta function, so I'm going to get rid of the integral. I'm going to get rid of alpha and replace alpha with t2 minus t1. This is the same as q, of course I have, minus c. And then I replace alpha with t2 minus t1. Then I have u of heavy side of t1. And here I'm also going to replace alpha with t2 minus t1, which ultimately means I also left with u of t1. And then I have this one, the last heavy side, which is going to be u of t2 minus t1. And of course, these two heavy sides are kind of redundant, so I'm going to write it slightly, little bit simpler. So that's pretty much how far I got with the cross correlation. So then I am ready for delving into the autocorrelation function of y. This also has put everything into the integral. It becomes somewhat long and nasty. Just write it all out. Q e to the power of minus c. Now I have t2 minus t1 plus alpha. You have t1 minus alpha of t2 minus t1 plus alpha. And then we have the h contributions, e to the power of minus c alpha, heavy side of alpha. So this is h of alpha. And everything else that you see here is Rxy evaluated at t1 minus alpha and t2. Now I can do a little bit of simplification at least. There are some things I can pull out of the integral, so let me at least do that. Q e minus c t2 t1, no alpha in that. Then I have filled in on the integral, and I have I have one c alpha here, and I have one c alpha here. Both are negative, so it's a e minus 2 c alpha. So u of alpha, u, or heavy side of t1 minus alpha, and Heaviside of T2 minus T1 plus alpha. Okay, so I need now to carry out an integral over 3 Heaviside functions. So this is kind of difficult to grasp by pure intuition, by pure just looking at this. So let us visualize what's going on here. So let me draw the real line, alpha, and then some y-axis, or whatever you want to call that. Yeah, you can call this T1 here, T2 there, and then I also need this point, which is minus T2 minus T1. Okay, so let me first perhaps look at this Heaviside function. How does this one behave? Well, this one has a step in origin. So it goes like this. Then, how about the second Heaviside? How does this one behave? Well, what I have here is not alpha minus T1, but T1 minus alpha. So what I have here is basically flipping the Heaviside function around T1, flipping it around T1. So that means that this one should be going like this. Then I have one more Heaviside function. I'm going to show that one in green. So that's this one, and this I could also write as alpha minus T1, 2 minus T1. Now, if I assume that T1 is larger that T2 is larger than T1, then this one will be going like this. Okay. Yeah, I have to make that assumption, but that doesn't use any generality. I can swap that back and forth. Anyway, when I make that assumption, then we see that the green one, the last Heaviside, is of no importance, because this Heaviside, the first one, kills everything that is below 0. And this second Heaviside kills everything that is above T1. This means that what I'm left with is the following. So I have still stuff I had from side integral, T and the exponential in T2 and T1. Then I'm integral from 0 to T1, e to the power of minus 2 Ca dA, alpha, sorry. And this is not a very difficult integral to evaluate. So what I end up with is this. T2 minus T1. If T2 is say larger than or equal to T1. So then we have an expression for the autocorrelation function of a Gauss Markov process. Now, one thing that is interesting to notice here is that this is also not a stationary process. which is kind of expected because we did send in a non-stationary process, so we wouldn't expect to get anything stationary out of it. Why is it non-stationary? Well, it's because of this term, e to the power of minus c t1. There's no way we can get that onto the form t2 minus t1, so it has to be non-stationary. If this part was not part of it, then we would only have this constant q divided by 2c, and then we will have this exponential. So, and this exponential is t2 minus t1, so that is stationary. So you see that the further away t1 goes from the origin, the more like a stationary process does this behave. So if you have a system that has been turned on for a long time, you can just as well consider that as a stationary system. And something you often want to know is the value R00 or RTT, the function, the variance at a given time. And you see that that will always be given by this constant. Well, again, as soon as this term goes towards 0, it will be this constant that gives you the maximum. So then you have a formula for the strength of the noise that is being generated by a gauss markov process, which, for example, could be the average strength of a bias in an inertial navigation system.